Imagine stirring a cup of tea. Now, imagine stirring a pot of golden syrup. The difference you feel is viscosity. It's a measure of a fluid's resistance to flow, a kind of internal friction. Water, with its low viscosity, moves freely and easily. The golden syrup, thick and sticky, resists your spoon with a sluggish reluctance. This simple property is fundamental to understanding how everything in the universe, from the water in our rivers to the vast clouds of gas between stars, moves and behaves. It's a force that dictates the shape of splashes and the speed of streams, a silent choreographer of the fluid world. This internal friction arises from the interactions between the molecules within the fluid. In a low viscosity fluid like water, the molecules glide past one another with relative ease. In a high viscosity fluid like honey or engine oil, the molecules are more strongly attracted to each other, creating a drag that slows the entire system down. This stickiness is not just a curiosity, it's a critical property. It's why oil can lubricate the moving parts of an engine, creating a protective film that prevents metal from grinding against metal. It's also why lava flows can be so devastatingly slow yet unstoppable, as their immense viscosity allows them to creep forward with immense power. Consider the simple act of pouring. Water splashes and tumbles out of a glass with chaotic energy, a beautiful, fleeting spectacle. Pouring honey, however, is a different story altogether. It coils and folds in on itself, forming elegant, looping patterns as it descends. This graceful, almost deliberate motion is a direct consequence of its high viscosity. The fluid's internal resistance dampens the chaotic tendencies, forcing it into a more ordered and predictable flow. From the kitchen to the cosmos, this single property governs the character of fluid motion, shaping the world in ways both subtle and profound, and revealing the underlying physical laws that connect a simple breakfast table to the grandest galactic structures. The importance of viscosity extends far beyond our everyday experiences. In biology, the viscosity of blood is a critical factor for our circulatory system. If blood were too thin, it wouldn't transport oxygen and nutrients effectively. If it were too thick, our hearts would struggle to pump it through our intricate network of veins and arteries. In geology, the viscosity of the Earth's mantle, which flows on geological timescales, drives the movement of tectonic plates, shaping the very continents we live on. It is a universal parameter, a number that tells us a story about connection and resistance, a story written in the language of physics. When a fluid moves, it can do so in two primary ways. The first is what we call laminar flow. Picture a slow-moving wide river on a calm day. The water seems to glide along in smooth, parallel layers, or laminae. Each layer slides past the one next to it with minimal mixing. This is a state of order and predictability. It's the kind of elegant, serene motion you see when you turn a tap on just enough for a steady, clear stream of water to emerge. This flow is beautiful in its simplicity, a physical system behaving with a quiet, mathematical grace that we can easily describe and understand. Then there is the other state, turbulence. This is the universe in a more chaotic and energetic mood. Turn that tap on full and the smooth stream shatters into a churning, frothing mess. This is turbulent flow. Instead of orderly layers, the fluid is filled with swirling eddies and chaotic vortices that appear and disappear in an instant. Think of a raging waterfall, the smoke billowing from a chimney on a windy day, or the cream swirling chaotically into your coffee. This is a world of complexity and unpredictability, where the fluid's motion is a dizzying dance of interacting, random-seeming patterns that are incredibly difficult to pin down. The transition from laminar to turbulent flow is one of the great unsolved problems in classical physics. It isn't a simple switch from one state to another. It's a complex process where small disturbances in a smooth flow can suddenly grow and cascade into full-blown chaos. Viscosity plays a crucial role here. A highly viscous fluid, like our golden syrup, tends to dampen these disturbances, favoring smooth laminar flow. A low viscosity fluid, like air or water, is far more susceptible to tumbling into turbulence. It's a battle between the fluid's inertia, its tendency to keep moving, and its viscosity, its internal friction trying to calm things down. This distinction is not merely academic, it is vital for almost every field of science and engineering. The smooth, laminar flow of air over a glider's wing generates lift with maximum efficiency. Turbulent flow, on the other hand, creates drag, slowing an aircraft down and wasting fuel. Yet sometimes turbulence is exactly what we need. The turbulent mixing of fuel and air in an engine is essential for efficient combustion. Understanding when and why a flow becomes turbulent is therefore a quest to understand one of nature's most common, yet most mysterious behaviors. It's a challenge that takes us right to the heart of modern physics. So, how do we describe this wonderful, complex world of fluid motion? How can we predict whether the air flowing over a wing will be smooth or chaotic? The answer lies in a set of equations of profound importance, the Navier-Stokes equations. These are, in essence, Newton's second law of motion. Force equals mass times acceleration, but rewritten for fluids. They are a mathematical description that connects a fluid's velocity, pressure, temperature, and crucially, its viscosity. They are the rules that govern every drop of rain, every ocean current, and every wisp of cosmic gas. At their core, the Navier-Stokes equations are what we call partial differential equations. This sounds intimidating, but the idea is quite simple. Instead of just describing how something changes over time, they also describe how it changes from one place to another within the fluid. They account for several distinct forces. There are pressure gradients, which push the fluid from areas of high pressure to low pressure. There are viscous forces, our internal friction, which resist motion and smooth out differences in velocity. And finally, there is inertia, the term that describes the fluid's own momentum, its tendency to keep doing what it's already doing. The beauty of these equations is their universality. The very same mathematical framework can be used to model the air flowing around a Formula One car, the currents circulating in the deep ocean, and the blood pumping through an artery. You simply change the parameters, the viscosity and density of the fluid, the geometry of the space it's flowing through, and the equations will provide a prediction of its behavior. They are the closest thing we have to a unified theory for the classical world of liquids and gases, a testament to the power of mathematics to capture the intricate workings of nature in a few elegant lines of symbols. However, their elegance hides a formidable challenge. The inertial term in the equations is nonlinear. This means that the different parts of the flow affect each other in complex, looping ways. The velocity of the fluid affects the forces, but the forces in turn affect the velocity. This feedback loop is the mathematical seed of chaos. For smooth, laminar flows where viscosity dominates, we can often simplify the equations and find precise, exact solutions. But when inertia takes over and the flow becomes turbulent, these non-linear interactions spiral out of control, making the equations phenomenally difficult to solve. The immense difficulty of solving the Navier-Stokes equations for turbulent flows has not stopped us from using them to engineer our modern world. We simply use the most powerful tools at our disposal, supercomputers. By breaking a large volume of fluid, like the atmosphere around the Earth or the air around an aeroplane, into billions of tiny, manageable cells, we can use computers to approximate the solutions. This is the foundation of computational fluid dynamics, or CFD, a field that has revolutionized design and forecasting. It allows us to run virtual experiments that would be impossible or impossibly expensive in the real world. Think about the design of a modern passenger jet. Engineers must understand precisely how air will flow over every inch of its surface. Using the Navier-Stokes equations, they can simulate the airflow around a new wing design on a computer, identifying areas where drag-inducing turbulence might form. This allows them to refine the shape, optimizing it for fuel efficiency and safety long before a single piece of metal is cut. The same principles apply to the design of racing cars, where managing airflow to create downforce is the key to cornering at incredible speeds. Every sleek curve is a product of these calculations. Perhaps the most ambitious application of these equations is in weather forecasting. The Earth's atmosphere is a vast, turbulent fluid system driven by the energy of the sun. Weather prediction models solve the Navier-Stokes equations on a global scale, taking in data on temperature, pressure, and wind from satellites and weather stations. The computer then calculates how this massive fluid system will evolve over the next few hours and days. The iconic swirling patterns of a hurricane on a weather map are, in effect, a visual solution to these equations. A picture of nature's beautiful and sometimes terrifying fluid dynamics in action. The quest to fully understand the Navier-Stokes equations remains one of the greatest challenges in science. The Clay Mathematics Institute has offered a $1 million prize for a mathematical proof that sheds light on their behavior, specifically in the realm of turbulence. Solving this problem would not just be a triumph of mathematics, it would deepen our understanding of the universe itself. From the smallest ripple to the grandest storm, the motion of fluids is a constant, beautiful presence in our lives. The Navier-Stokes equations are our most powerful tool for understanding this intricate dance, reminding us that even in the chaos of a storm, there is a deep and wondrous mathematical order